Good morning, everyone. I am Kevin Hanicombe. I am an aerospace engineer here at the University of Central Florida, and I'm excited to present our project of Glide and Tow Airdrop. We are the tow team capable of towing the glider to an altitude of 200 feet. But before I begin presenting, I'd like to give a moment to my team to present themselves as well.
Hi, my name is Michael Cornett, and I am studying mechanical engineering.
Hi, my name is Bradley Joseph, and I'm studying aerospace engineering.
Hello, I'm Nicholas Stan, aerospace engineer, class of 2023.
Great. Without further ado, I'd like to get started on this interesting project. So at its core, this project rotates around developing a novel attachment mechanism to couple the tow and glider aircraft together. So we took a different approach to this based on the literature surrounding the community. Most prevalent is the one in NASA that we can see down here. So NASA kind of took a more, as this project would call it, Remora style coupling mechanism, where the space shuttle directly attached to the top of an aircraft. And initially in the NASA program, they would detach the space shuttle from the aircraft just to test its flight characteristics. So similar to what we're doing, except completely dedicated to that profile. So that's one of the main mission default parameters is to quickly attach and detach this, similar to missiles on aircrafts and aircraft carriers like F-15s, different fighter jets, for instance. So we took all these parameters and kind of combined them into one. Particularly Nicholas, he focused on this, as we can see on his design over here on the bottom right. So this latch will open and close easily, and it's spring-loaded, and it has just some serverless mechanism holding them in place. So this is by far the most intriguing part of the project. There's a bunch of cool stuff that we'll get to. So we can see some of the results here that we've gone. We've been able to attach, detach within 3 seconds, which the mission default was 15 seconds. So we can see a great improvement there. So before we get into the nitty-gritty technical aspects, I feel like it would be great to go over the game plan that this research kind of went to fulfill. So core to any project, we begin by analyzing the current literature in the community. We derived initial plane aspects with formulas and theories taught in our classes, for instance, thin airfoil theory, or the surface tail taught in surface size of the tail taught in flight mechanics. And this was all of iterative approach. And as we can see, there's multiple iterations here where we would present to our advisor, Dr. Hippelhauser, and after he gave us our input, we'd go back, change our design, and make sure we best fit to the mission profile. So as we can see, that kind of follows this suit here. So we go derive plane characteristics. We test through FEM and CFD. So virtual methods. We're not building anything yet. So after we get our confirmation, we see that we have a lift generated or we're structurally sound. We begin manufacturing. And then after we begin manufacturing, we could start physical testing. For instance, motor testing or lift testing in a wind tunnel, or even structural testing by breaking pieces of our plane, our initial prototype. Okay, so great. So we can see that's another iterative. So after that, we would rotate back around. If anything breaks or if it succeeds, we could go into flight tests, which we will begin this Tuesday, actually. So post this flight test, there's just a flight test by ourselves, just to make sure we could fly, and our flight characteristics match the mathematics predicted. We could start flight testing with the glider team. And then post this, we finish our design. Great. Woo-wee. Okay, now it's the part that I'm really excited about. I love the CFD stuff, and this was my main responsibility for the project, was the aerodynamic analysis. So one of the branches of the flowchart we mentioned prior. And to fulfill this, I took not a novel approach, but an approach I saw in many research papers where they used a universal enclosure. So we could vary the angle of attack without remeshing the plane inside ANSYS CFD fluid. So we could see we chose a mesh for the plane that was very fine, just to accurately model everything. And I should also mention that for the side slip testing, we basically took this universal enclosure and just flipped it on its side, just so we could vary the angle of side slip, and then get our side slip dependent parameters, similar to the longitudinal parameters and lateral parameters that we'll see on the next slide here. So we can see post this test for different varying speeds, range from 5 meters per second all the way up to 15 meters per second. Although that our CL and CD parameters, our coefficient parameters, are independent of velocity. So we could see that our CM alpha parameters here are fulfilled. That is that we have a positive CM0, that is intercept with the y-axis, and we have a negative slope here. So our stability parameter is fulfilled. As long as if we go over to the right, we see our stability parameters for the lateral modes of motion, roll and yaw. They're both fulfilled with positive slopes. So that was great. Now on to Michael's portion of the report, was FEM and the structural analysis to ensure the plane doesn't break in half during flight. So this was pretty cool. We could also see over here on the right that our max stress made logical sense. Those were all the longerons and ribs connected in our attachment mechanism for the wings to attach to the plane. Because of our wings being so large, that we had to develop a novel way to attach our wings to our fuselage to make sure we could transport it to the airfield and back from the school. So that's why we could see a very high stress, or in comparison to the rest of the plane, a very high stress over where this portion attaches. We could see, I should also mention that this FEM was obtained through integrating the coefficients of pressure derived through the CFD along the surface of the wing and along the surface of the plane, and the torque from the motor, for instance. And these were all input into the FEM to make sure we get an accurate result. So now on to the fun part. Another part that me and Nick was lucky enough to do was the physical testing. So we could develop thrust, not only static thrust analysis, but a dynamic thrust analysis. So the way we handled this test was as we could see, Nick modeled a CAD model for our propeller that was attached to a simple scale that measured in grams. And we turned and varied the throttle level for different static levels of thrust. And then Nick took his leaf blower and we blew it into the propeller. And this gave us data points that we could plot, or that I could take into MATLAB and fit a linear regression line. So now we figure out the slopes of each of these plots, which are a really cool aspect of these. Now that we have our force as a function of velocity, we are able to use Newton's second law, force is equal to mass times acceleration. And we know acceleration is this first derivative of velocity with respect to time. So now that we know our force is a function of time, we could integrate that force and figure out our velocity changing with respect to time, which is a really cool plot towards the end of this presentation that I'm really proud of. We could see a similar approach here for the lift, where Nick took his leaf blower and designed his own wind tunnel, which was a really cool part, and made sure we confirm our CFD even further. Our predictions produced via thinner airfoil theory, and this was a great aspect of the report, which confirmed the CFD results. And here's the part of the report I was talking about. So once we integrate this force as a function of velocity, we could see we could obtain different takeoff values, different distances to take off by combining the results from the CFD, that is our CL parameter. We know CL, we could set it equal to weight over dynamic pressure times the surface area of the plane, or the reference area of the plane, which for us is the wingspan area, wing surface area. And we could obtain for different varying weights of the plane its takeoff distance. So we could see once we hit certain velocities, we have enough lift to equal our weight. And we could also see over here on the right that we have a very optimal angle of attack, which actually coincided perfectly as planned with the theory, with angle of attack of 0 degrees. So as we're sitting at level flight, we're having our maximum CL/CD value, which is a great part of the project. It's hard to expand on how cool this project was and how much of a privilege it was to be a part in this short time span of 11 minutes that we're given. But I hope I was able to give some great insight onto what we were able to accomplish this semester. The whole team is very grateful to be here. Thank you for your time again to watch this video. If you have any questions, please leave a comment in the comment section below, and I'll try my best to answer it as fast as possible. Thank you. Have a great one.